I'm going to walk you through how to do radioactive half-life and decay calculation problems. So remember, as each nucleus in a radioactive piece of material decays, it becomes another type of material, and the material has less total number of radioactive atoms in it. So the number of decays in a time delta t is delta n, so it's the change in the number of radioactive nuclei, is equal to minus lambda times n, the number of particles you started with, times delta t. The minus sign tells you that the n is decreasing with time. Lambda is a decay constant that changes. It depends on which isotope you have. Some of them decay faster, those have a bigger lambda. Some of them decay slower, those have a smaller lambda. And remember, n is the number of radioactive nuclei. So if I solve that problem using calculus, what I get is that the number of particles as a function of time is equal to n0, the initial number of nuclei at t equals 0, times e to the minus lambda t, where lambda is the decay constant. We can also talk about the activity, which is the rate of change of particles, delta n over delta t. The SI unit is a becquerel for decays per second, is equal to the initial activity times e to the minus lambda t. And the initial activity can be found just by multiplying the number of particles you have times the decay constant. So as things decay, you have less and less nuclei in less and less radioactive nuclei in your material. And so if you look at the number of radioactive nuclei as a function of time, you can see it decreases exponentially, of course, because it's an exponential function. And if we look at the time that it requires to lose half of the radioactive nuclei, that is what we call the half-life. So in the picture here, you can see we start with 1,000. When we get down to 500, that's one half-life. After we have two half-lives, we've decreased that number of 500 down by a factor of 2 to 250. If we go another half-life, we decrease down by another factor of 2, so that's 125. Every time we have a half-life, we have half as many particles as we started with. The half-life can be found from the decay constant. It's just the natural log of 2 divided by lambda. Natural log of 2 is 0.693 approximately. And radioactive half-lives again depend on the isotope. It can be as small as 10 to the minus 22 seconds to as big as 10 to the 12 years. And as a nucleus decays, it's radioactive. It's not going to decay immediately to something that's stable. It's going to go through a bunch of different steps to various different radioactive nuclei until it gets to a small enough nucleus that it's stable. Each step in the process has its own half-life, and it can take many years, or it can take just seconds or milliseconds for it to decay to a new nucleus. Since we can tell how long different nuclei take to decay, we can determine the age of materials. So for example, something that's been alive will have carbon in it, and carbon-14 decays with time. So if we can measure what fraction of carbon-14 there is compared to carbon-12 in an object, we can determine how long it has been since that object died. So how long it has been since it stopped ingesting carbon. Carbon-14 dating is only accurate up to about 60,000 years. That's about 10 half-lives. After that, the amount of it becomes just so small you can't accurately measure it. For geological timescales, geologists use uranium-238, and that's how scientists have determined that the rock on Earth is about 4 billion years old. Okay, so let's do a couple of problems. All right, so if I have a basement, it's got some radioactive radon gas in it. I seal it off so that I can't get any more radon gas entering, and I want to figure out how many radon atoms are going to be left after 2 weeks. Is it safe for me to go in? So first of all, I need to calculate what's the half-life of radon. So let's look at the problem. I start off with 4.75 times 10 to the 7 atoms of radion. of radon. That's my N0. So let me go ahead and write that down. N0 is 4.75 times 10 to the 7. And the decay constant is, which is lambda, 0.181 per day. And you're going to see decay constants in per seconds, per days, per week, per year. And so you need to just be careful when you do your problem that whatever unit for time you use is consistent with what you have for lambda. So I want to find the half-life. The equation I'm going to use is the one on the bottom left. The half-life is the natural log of 2 divided by lambda, so 0.181. And when I put that in, I get that my half-life is 3.829 days. Okay, so just under 4 days to lose half of the number of radon atoms. So what I want to know is, after 2 weeks, how many do I have left? Well, 2 weeks is 14 days. So that's over 3 half-lives. So I should have, divide by 2, divide by 2, divide by 2. I should have less than 1/8 of what I started with. But let's do an actual calculation. So we want to calculate how many are left. And so we want to calculate using the equation at the bottom. N equals N0 e to the minus lambda t. I've got N0, I've got lambda, and I've got t. So my t is 2 weeks, which is 14 days. I'm going to leave it in days because my lambda is in days. So N is equal to N0 e to the minus lambda t. And now I just need to plug in my numbers. So 4.75 times 10 to the 7 times e to the negative lambda, 0.181, times time in days, 14. And I get that my number of particles is 3.77 times 10 to the 6 atoms. So it turns out I've gone down by more than a factor of 10 from where I started from. Okay, and equivalently, if we were also asked what the activity did, we would do a similar calculation. We would just use the activity decay equation. All right, let's do something with half-life and radioactive dating. So the Iceman has an activity of 0.121 becquerels, whereas a living organism has 0.231 becquerels. The half-life for carbon-14 is 5,730 years. So how long ago did the Iceman die? So the Iceman was a body that was found melted in a glacier up in the Alps over in Europe. And so they took a small specimen to do radioactive dating to figure out when he had his last breath, when he had his last meal. Okay, so what we know is we know his current activity, we know the initial activity. So we know delta N over delta T, we know delta N over delta T0, and we want to find T. We know the half-life for carbon is 5,730 years. So that's going to give me what the lambda value is. So if you look at the equation in the middle at the bottom, I've got everything except T. I just need to arrange it to pull out the T. So how am I going to do that? Well, what I'm going to do is I need to rearrange that equation. So I've got delta N over delta T is equal to delta N over delta T0 times e to the minus lambda T. I want to pull the T out of there. Okay, so what I can do is just to make the algebra look a little simpler, I'm going to put in my initial and my final values for the activity. All right, so first, if I want to get the t out of the exponential function, I need to get the exponential function on one side all by itself. So I'm going to divide the left-hand side. So I get that e to the minus lambda t is 0.121 over 0.231. Okay, so now if I want to get the t, now I got to get it out of the exponential function. And the way to do that, to get anything out of the argument of a function, is to do the inverse of the function. What's the inverse of the exponential function? It's the natural log. If I take the natural log of e to the x, I just get the argument x out. So I need to take the natural log of each side. So the natural log of 0.121 over 0.231 is equal to, on the other side, I'm just going to have minus lambda times t. And now I'm ready to get my t, right? So the t is just going to be this natural log divided by minus lambda. So t is going to be equal to natural log of 0.121 over 0.231 divided by my minus lambda. Okay, so I can put in the numerator in my calculator. I need to calculate my lambda. How am I going to calculate my lambda? Well, I know the half-life, so I know that the half-life, t1 half, is equal to natural log of 2 over lambda. So that means lambda is equal to natural log of 2 over the half-life. And the half-life is 5,730 years. So I get that lambda is equal to 1.21 times 10 to the minus 4. And what are our units going to be? They're going to be per year, so years to the minus 1. So now our lambda is in units of years, so that means that the time I get when I put my number in down in my equation at the bottom is also going to be in years. So I'm going to take the natural log of 0.121 over 0.231, which is going to give us a negative number. Natural log of anything less than 1 is going to be negative, divided by negative lambda, minus 1.21 times 10 to the minus 4. So I've got a negative over a negative is going to give me a positive. I get 5,347 years. So just less than one half-life has been the time since the Iceman died. So that's the most complicated problem involving radioactive dating, is to do the algebra to rearrange to get the time out of the exponential function. So what problem do I want you to do today? Well, I want you to basically duplicate what I just did. So I'm told you the half-life of oxygen 15 is 122 seconds. How long does it take for the number of oxygen present to decrease by a factor of 10 to the 4? So in other words, if it was initially 10 to the 8 oxygens present, it goes down to 10 to the 4. You might use those as your n0 and your n values to calculate, rearrange, and get the time out of the argument of the exponential.